Welcome to the next major section of our course, Data Visualization. We have learned how to collect, clean, and analyze data using NumPy and Pandas. Now, we must learn how to communicate our findings visually. Maybe the most fundamental and widely used plotting library in Python is Matplotlib. 1. What is Matplotlib? Matplotlib is a comprehensive library for creating static, animated, and interactive visualizations in Python. It is designed to be highly customizable, allowing you to create publication-quality figures, charts, and plots. Think of it as the original core drawing tool for Python data science. 2. Why visualize data? While statistics like the mean and standard deviation are useful, they can often hide critical information. Visualization helps us identify trends, patterns, and outliers that are invisible in raw data tables. A well-designed plot can communicate complex information almost instantly. Before importing, you must install first. You open your terminal and run this command. 3. The PyPlot module. Matplotlib is a very large library, but almost all introductory plotting is done through the pyplot submodule. This module provides a simple interface that is modeled after MATLAB, making it straightforward to generate figures and axes. Standard practice is to import it using the alias plt. 4. The plotting workflow. The basic workflow is simple. First, prepare your data, typically using NumPy or Pandas structures. Second, use a plt function, such as plt.plot, to define the visual elements. And third, use plt.show to render and display the final figure. To summarize, Matplotlib and pyplot are our tools for visualization. Our next lecture 37.02, Create Project. See you there. Welcome back. Before we can draw our first chart, we need to set up our project environment. Since Matplotlib relies heavily on numerical data, we will import both Matplotlib's pyplot module and NumPy to efficiently create and manage the data we are going to visualize. 1. Project setup and file creation. Start by creating a new folder named matplotlib_projects to house all our visualization work. Inside this folder, create a new Python file named charts.py. We will write all our code in this file for the next few lectures. 2. The essential imports. The two import statements shown are the foundation of nearly every Matplotlib project. We import matplotlib.pyplot and commonly give it the alias plt. We also import NumPy as np, as its array generation capabilities, like np.arrange and np.linspace, are ideal for quickly creating sample data for plotting. 3. Writing the project boilerplate. For simplicity, we establish a basic code structure right away. We define simple X and Y data using NumPy, followed by placeholders for the plotting and showing functions. This three-step structure, data, plot, show, will be repeated in every plot we create. To summarize, set up your file with the necessary imports and the basic three-step structure. Our next lecture 37.03, Generate Line Plot. See you there. Welcome back. In this lecture, we generate our first actual chart, the line plot. Line plots are the standard for visualizing time series or trends where data points are connected in sequence. We will use the main plotting function in the pyplot module, plt.plot. 1. Preparing X and Y data. For a line plot, you need two sequences of the same length, X values for the horizontal axis and Y values for the vertical axis. We use NumPy's linspace to generate 50 evenly spaced points between 0 and 10 for X, and then calculate the sign of those X values for Y. It is crucial that both arrays have exactly the same length and correspond element by element. Two. Generating the plot. The core plotting function is simple, plt.plot. You pass the X array first, followed by the Y array. This function internally creates the figure and draws the line by connecting the corresponding X, Y points. However, calling this function does not immediately display the output. 3. Displaying the plot. To actually render and display the generated chart, you must call plt.show. This function executes the plotting commands, opens a separate window showing the figure, and stops the execution of the code until the window is closed. Always remember to call plt.show at the end of your plotting script. To summarize, the three-step process data, plot, show is the foundation. Our next lecture 37.04. Add color and grid. See you there. Welcome back. While the basic line plot works, it often lacks visual context. In this lecture, we learn how to significantly enhance readability by customizing the line color and style, adding markers to highlight data points, and including a grid to help estimate values along the axis. 1. Setup. Basic line plot data. We begin with a simple parabola function. This straightforward dataset will help us clearly see the effect of various styling arguments we apply to the line plot. 2. Customizing line color and style. You can control the appearance of the line using keyword arguments within plt.plot. Use color to set the line color, using either English names like green or hexadecimal codes. Use line style to set the line pattern, such as a dashed line represented by two dashes. Finally, use marker to place symbols at each data point, such as O for a circle. 3. Adding a grid. To make it easier for viewers to estimate the values of points, we can add a grid to the background of the plot using plt.grid and setting its argument to true. This adds horizontal and vertical reference lines extending from the tick marks on the axis. This should be called before plt.show. 4. Displaying the enhanced plot. Running the code now displays the plot with all our customizations, the green, dashed line, circle markers, and the background grid. You can see how much more informative the plot becomes with these simple additions. To summarize, these simple style elements greatly improve plot clarity. Our next lecture 37.05. Control transparency. See you there. Welcome back. When plotting multiple datasets, especially when lines or markers overlap, it can be difficult to distinguish individual elements or see where data points are densely clustered. In this lecture, we introduce the alpha parameter, which controls the transparency of any visual element, a simple yet powerful tool for handling overlapping plots. 1. Defining overlapping data. To properly demonstrate transparency, we need data sets that overlap. We use number py to create 3 different y-series: sine, cosine, and tangent, all based on the same x data. These 3 lines will naturally intersect multiple times. Two, using alpha for transparency. The alpha parameter takes a floating point value between 0 and 1, where 1 is the default, fully opaque setting. We plot the 3 lines with progressively lower alpha values. Notice how the blue line with the default alpha of 1 completely obscures anything underneath it. The red and especially the green lines with lower alpha values allow us to see the other lines where they overlap. Three, adding a legend. Since we used the label argument in our plot calls, we can easily generate a legend using plt.legend. The legend shows the color and style of each line and its corresponding label, which is essential for identifying which transparent line is which. Running this code now shows the final visualization. To summarize, the alpha argument is key for clarifying plots with high data density or many overlapping series. Our next lecture 37.06, Generate Scatter Graph. See you there. Welcome back. While line plots show trends over a continuous range, scatter plots are ideal for visualizing the relationship, correlation, and distribution between 2 different variables. In this lecture, we switch from plt.plot to the dedicated function for point data, plt.scatter. 1. Preparing data for scatter plot. We generate 50 random data points for x and y. Crucially, the scatter plot is powerful because it allows the size and color of each individual point to be controlled by 2 additional independent variables. We create colors and size arrays for this purpose. Two, generating the basic scatter plot. The syntax for plt.scatter is similar to plt.plot. X data first, then Y data. Unlike the line plot, the scatter function draws unconnected markers at each X, Y coordinate. 3. Controlling point size and color. To use our auxiliary variables, we pass the size array to the S argument, making each marker proportional to its corresponding size value. We pass the colors array to the seeth argument, allowing the color of each point to map to its color value according to a defined color map, such as Voridus. We also add transparency using alpha to better visualize overlapping data points. This creates a powerful 4-dimensional visualization: X, Y, size, and color. To summarize, scatter plots are excellent for exploring multidimensional data visually. Our next lecture 37.07, Bar Graph. See you there. Welcome back. Bar graphs are the gold standard for visually comparing the magnitudes of discrete categories. Unlike line or scatter plots, bar graphs plot categorical variables on the x-axis and their numerical values or frequency on the y-axis. We will use the plt.bar function to generate these plots. 1. Preparing categorical data. To plot categories, we need two things: the category names or labels for the x-axis and the numerical values for the height of the bars. Matplotlib's plt.bar requires numerical positions for the bars, so we use numpy's arrange to create a simple sequence x_pos that corresponds to the number of categories. 2. Generating the bar plot. We call plt.bar, passing the numerical positions x_pos and the values. We use the width argument to control how much space each bar occupies. A value of 0.8 is standard. We also specify the color. At this point, the x-axis still shows the numerical positions 0, 1, 2, 3, not the category labels. 3. Labeling the x-axis. To display the actual category names, we use the plt.xticks function. This function takes two arguments. First, the positions where the ticks should appear, which is x_pos, and second, the corresponding categories, text to be placed at those positions. We then add a title and y-axis label before showing the final, correctly labeled graph. To summarize, bar graphs require careful handling of numerical positions and categorical labels. Our next lecture 37.08, histogram. See you there. Welcome back. While bar charts compare categories, the histogram is specifically designed to show the distribution of a single, continuous numerical variable. It allows us to see how frequently different values or ranges of values occur in our dataset. We use the dedicated function plt.hist for this visualization. 1. Preparing continuous data. Unlike previous plots that needed both x and y arrays, a histogram requires only one continuous array of values. We generate 1,000 random data points that follow a standard normal distribution, meaning most values cluster around 0. This is perfect for illustrating distribution. 2. The role of bins. The core concept of a histogram is the bin. The range of the data is divided into intervals or bins. The height of each bar in the histogram represents the count, the frequency, of data points that fall into that specific bin interval. The number of bins directly controls the shape and detail of the resulting plot. 3. Generating the histogram. We generate the histogram by calling plt.hist and passing our data array. By default, Matplotlib will choose an optimal number of bins, typically 10, for the visualization. We add a color and alpha for better visual appeal. Running this shows the classic bell curve shape of the normal distribution. 4. Customizing the number of bins. If the default setting lacks detail, we can specify the exact number of bins using the bins argument. Setting bins to 50 provides much finer resolution, revealing more minor fluctuations in the data distribution. Choosing the right number of bins is a balance between smoothing out noise and retaining important details. To summarize, histograms are essential for understanding data shape. Our next lecture 37.09, Plotting Subplots. See you there. Welcome back. This is the final lecture in our Matplotlib section. Until now, we have plotted only one chart per figure. However, a common requirement in data analysis is to show several related visualizations side by side. Matplotlib provides the plt.subplot function for precisely this purpose, allowing us to create multiple plotting areas, called axes, within a single figure. 1. Understanding subplots. When you plot in Matplotlib, you are always plotting on an axis object which lives inside a figure object. The plt.subplot function allows you to define a grid layout for these axes. The function takes 3 integer arguments: the total number of rows, the total number of columns in the grid, and the plot number that you are currently activating. 2. Setting up the plotting grid. We first prepare our data, 3 different Y arrays based on the same X values. We want to display these 3 plots in a single figure using a 2x2 grid layout, which gives us 4 potential slots. Three. Plotting the first 3 subplots. We call plt.subplot before each plot. For the first plot, we use plt.subplot 2, 2, 1, meaning a 2x2 grid, activating the first position. Any subsequent plotting functions, like plt.plot or plt.title, will target that active subplot. We repeat this process for positions 2 and 3. Notice that we use the shorthand notation to set color and line style simultaneously. Four. Displaying the composite figure. Finally, we use plt.tight_layout to automatically adjust the spacing between subplots, ensuring titles and labels don't overlap. Then, plt.show displays the figure containing all 3 separate, labeled plots. To summarize, subplots are essential for comparative visualization. This completes our Matplotlib section. You now know how to analyze data with pandas and visualize it with Matplotlib. Our next section is in built data structures, starting with lecture 38.01. Introduction. See you there.